Hello, this is Getting Miles. I just wanted to make this quick video explaining how eigenvectors are used in PCA, or principal component analysis. It's really not that complicated, but bear with me on this one a little bit. I believe a lot of things in data science, we use these big words and it kind of covers up what it's saying. It's actually very simple. Principal component analysis is a technique that's used to reduce dimensionality in data. Dimensionality just means the number of factors we're using in trying to predict something. So sometimes in our data set, we have tons of information, dozens of columns, hundreds, thousands of columns. And that's really computationally intensive to try to bring that all into a model. And sometimes it creates an overfit model where we're really too dialed into all the noise in the data that we think might be insightful in the terms of our training data, but isn't in the terms of the real world. So PCA, or principal component analysis, helps us find the most relevant factors. So we can take it down from thousands of columns to maybe 20 or 100 columns. And that's much more computationally cheap, right? You can do it much faster, and it can still give you a really good model. So the way it works under the hood, that's what we kind of talk about on the top, but to kind of get under the hood a little bit, it's used what's called eigenvectors and eigenvalues. This is a little bit of linear algebra, but it's fairly simple. An eigenvector is, in the context of kind of physics, a vector would be talking about the direction of forces going in. So if you've ever seen Despicable Me, right? A vector's talking about something with both direction and magnitude, right?
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
It's the same idea. This line is moving in a direction, and it has a certain magnitude, right? It has how much force is it moving in, if we're talking in a physics context. In data science, we're trying to say, how strong is this relationship in this direction? So you can say, oh, wow, this data set has a pretty strong component that's describing its spread or its variance, how the data spreads. It has a pretty strong component in this direction. That indicates this is maybe a principal component, right? So the data, what this algorithm does is it just quantifies all the different vectors that this data set has, in all the dimensions it has. So in this case, there's only two dimensions, right? X and Y. So you can say, hey, this data has two primary components. One seems to be in this direction, one seems to be in this direction. This one is bigger. This one explains more of the variance, so it's a more principal component. And it'll do that for the top or whatever. It'll arrange them all by how strong of a component it is, and then keep it, right? And so that's the eigenvector and eigenvalues, right? The eigenvector tells us how strong that line is. And then it just does it for all of them in a multi-dimensional space. So in this one, it's two-dimensional, right? We can visualize two dimensions. If you have 150 different columns in your data set, there would be 150 different dimensions in your data. And it would be doing the same idea with these two arrows, but in 150 dimensions, which we can't really visualize. But just imagine this times 150 other arrows and going in different directions. And then it just picks the best ones, the ones that have, again, the strongest relationship, or the one that explains the variance, how the data is varying the most. And then picks those and comes back with a much more simple data set. It says, hey, we have only these ones because these are the only principal components. It's a really useful tool that uses math to quantify what is the best one automatically without you having to go through and individually check each one. If you want to get some more detail on this, 3 Blue 1 Brown has a great video on linear algebra. There's some MIT open source software. Of course, it's kind of explaining it. It's really amazing. Little simple bit of machine learning that makes it seem like magic, but it's actually just really basic math. It's the same idea as if you went through and graphed each one of these, try to put a line of best fit to describe everything. That's kind of the same idea, right? And it does it for all the different dimensions, and then figures out which one has the highest values and use those. So anyways, that was my quick introduction on principal component analysis. I hope it was helpful. these things are all, again, they're not quite as magic as we make them out to be. I love this idea that we're all kind of grumpy wizards trying to cast these data cells, and people don't quite understand what's happening under the hood. They just know, oh, well, PCA reduces dimensionality, but knowing how and why is really helpful, and understanding kind of the tools you use. It kind of prevents data science from being wizardry that the practitioners don't fully understand. They just know that PCA good, and we should do that. Yeah, anyways, so I just wanted to throw that out there, and I hope it's helpful to you.